Okay. So we were discussing different types of channel. The next type we want to see is what is called classical. We have already seen this. Classical quantum channel. So this is just a map from a classical space to a quantum space. That's all. So basically this is if you have an algebra which is commutative, you want to take it to MMC basically. But we define it in a different way. So you have some set. This is some set. Then you have a Hilbert space HA is equal to span of this X, all these vectors, X in this set. Then you know that on this L of HA, our classical space, it is diagonal algebra. So the N classical to classical quantum channel from whatever A to B or whatever, from A to B, okay, of any XX, we just want this equal to some sigma X, where sigma X is in L of HB. So it takes this to this. Or it takes, I mean, delta X prime, you can take a delta X and X prime. So in particular, N of A to B, whatever, classical quantum channel of any row or any T also, any T is going to be, so any T is going to be, N of T is going to look like this, right? T of X prime X, okay, and then X. Is that right? What I have written? Okay, summation X. Is that right? Correct, right? This is how it will look. This is the matrix entry, and there is the partial isometries, okay? Matrix units. So you can take the summation out. So you can take the summation out, and n acting on this only you will get, and only when x equal to x prime that has any meaning. I mean, that's non-zero. So this is just going to be summation x in this, x in this. Then you get x, t, x, sigma x. That's all. Put it in the top. Okay. That's all. So this is the classical quantum channel. So to see that this is a possible, I mean, we can, I mean, it's actually clear. We will find. So what it does is the following: in the state space, if you have a problem, I mean, so there are two ways of describing classical probability space. One is the, one is in the as functions, which are just diagonal matrices, or as probability distributions, which are also diagonal matrices, states with probability distribution in the diagonal. So it will take any probability distribution, P1 up to Pn, whatever, Pn, it will go to summation Pi sigma P min, whatever. Pi, I mean, it should be X. It will take any probability distribution Px or X in this to summation Px sigma X. That's what it is. So we can compute the Krauss operator. Krauss operator, it has to land in B. So, I mean, suppose if sigma X is positive operator, so it will look like summation lambda X J and then some xi X J, xi X J. Okay. Suppose if it look like this, like spectral theorem. Okay. Then take K X J equal to, so it has to land in Xj, okay. So it will just land in B. So this is B. Okay. These are all operators in B. Okay. This is happening in B. I write B because it's happening in B. Okay. So xj B So it should take inner product with A. So that's the A. And square root of lambda Jx. Okay. Then for any row in LFHA, this is just going to be Kxj summation over x and j, x and this, and j is up to j equal to 1 to r. Okay. So the summation j equal to 1 to r, kx and then row, then kxj star. So you get 2 times this, so it will be lambda xj. It will become lambda xj. Then xj x will be there. So that the inner, it will take the inner product. I mean, this will be hit by x and 2 times x and sorry. X not equal to x prime, it is what do we get? We get xi summation. We get the summation, and we get xi a x, xi x, and then x, and then rho, and then x here. Then it will be x only. I was wondering. I mean, we are having the same x here. So I was wondering x prime and y, how it will work. It will be x only. So we get x here, and then we have this xi xj. Okay, summation over x and j. Okay. Now this is a scalar. You can tell this is a scalar. You can just take it out. So this is summation over x, rho x, okay, and then summation over j, lambda xj, xi xj, and which is just, this is just that sigma x. Sigma x. This is what we want. So these are the Krauss operator. These are the Krauss operator. Okay. Notice that this is a rank 1 operator. The Krauss, they are rank 1 operator. Okay. So these are the Krauss operators, which are rank 1 operators, and from that we get. Okay. So we will use it because for entanglement breaking channel, the necessary and sufficient condition should be the Krauss operator should be given by rank 1 operator. So that's why we notice this, we observe this. Okay. Okay. And to see that this is a quantum channel, so it's, I mean, we got the Krauss operators and we showed that they are the Krauss operators, so that's completely positive. So it should be preserving trace. To see that it preserves the trace, you can either compute this, I mean summation k xj, no, x in the top, xj star k xj. This should be equal to 1. Okay, you can actually directly compute it, right? I mean, I don't have to write, I believe. So, everything is finite here. So if you just take the star of this, you get x here, and then you get xi xj there, and that with the lambda g will give the trace of this. I mean, so it will be clear. That will be, I mean, that will, I mean, that if you just flip this, I mean, you have the star of this, that will become x will come here and jx will come here, and lambda j that will add up to 1. Then it will be summation xx. Summation xx, their orthonormal basis is 1, identity operator. Okay, so this is identity operator. Okay, so it's an exercise, easy exercise. Okay, you can just flip it and compute it. You just have to use, I mean, maybe you can write it. So this is just going to be summation over that lambda xj, okay, and then xi, it will be this, right? X times xi xj, okay, xi xj, and then x here. and that will, because the trace of that, I mean, sigma x is the state, because sigma x is the state, so the trace of that is 1. So this will add up, this lambda j times this will add up to 1. Okay, so this is the summation xx, which is equal to identity operator. Okay. So this is the Krauss operators. From these Krauss operators, you can construct the what is that, Stein spring. It is just that you have to append Hilbert space of dimension r, and then you can compute. Okay, you write it. That's an exercise. Okay, so the Choi matrix NCQ, the classical quantum channel Choi matrix. Choi matrix is 1 tensor n of this, right? I mean, here we are assuming that, I mean, Choi matrix depends on the orthogonal. It actually doesn't depend on the orthogonal basis in one sense. See, Choi matrix is the following. If you have I, J, okay, tensor I, J. Okay, Choi matrix is 1 tensor, whatever the n is of this summation. Okay, you have a summation, you can take the summation of. Okay. This is what the Choi matrix is. So, which is same as saying 1 tensor n acting on this. This is the maximal entangled state gamma gamma. So a maximal, I think we have gone through this. A maximal entangled state is just this, which is just I tensor ij, I mean gamma gamma. That's right, which is just I tensor I, right? Gamma is I tensor I. So this will be I tensor I mean ij tensor ij. Okay, but okay, ij tensor ij. Okay. So you see, gamma should be equal to, you know this, 1 tensor x of gamma is same as x transpose tensor 1 tensor gamma. This is a thing we have noticed. Okay, so this will imply that if you have a unitary u is unitary, then 1 tensor u will be u transpose. You get u transpose. So if you have u bar there, so this is true. U bar tensor u of gamma should be equal to gamma. Right? You will get a u transpose here, and u transpose, if you put a bar, I mean, which is just a star of the, I mean, its bar is the star. So it will be, instead of you have u bar of that, then that will also be equal to 1. Right? So this is true. So it is just 1 tensor 1 of gamma, if you just bring the u here. Okay. So because this is true. So in particular, so if Ek is any orthonormal basis, here gamma is defined with respect to standard orthonormal basis. The IO 0 to I minus 1, 0 to the dimension minus 1. Okay. So the Ek is any orthonormal basis, then this gamma is also equal to Ek bar tensor Ek. If you apply U bar on this, Ek to Ek bar, I mean, if U of I equal to Ei, U of I equal to Ei, then this gamma is also Ek bar tensor Ek, because U bar of this is Ek bar. Ek bar is just, you have the entries and the coordinates, you just put a bar over everything. That's what Ek bar is. It's not like star, it's just putting a bar over. Okay, so this is Ek bar tensor this. So gamma is same as this. So now you have defined the Choi matrix in terms of gamma. Okay, so instead of this orthonormal basis, you can't take any other orthonormal basis Ek, but you have to take Ek bar tensor Ek. Then it works for any orthonormal basis. Okay, Choi matrix you can define in terms of any orthonormal basis, provided if they are, I mean, if they are real entries, then it will be the same. Okay, so that's what. So what I am saying is you can take x itself. Okay, here. So summation. So what will get xx? I mean, xx bar will get tensor xx bar. Right? Summation over xx bar. And only when n is when x is, I mean, only when x bar equal to x, it is good. So this will imply xx tensor sigma x. This is the Choi. So this is the Chai matrix of the classical quantum channel. So which is just you have a classical thing outside. I mean, in this one tensor part, and you have sigma x and the other one. Okay, so I erase this. Okay, so the next one is, so I have said about classical quantum channel. Next one is quantum classical channel. So this takes a quantum state to a classical state, which you have already seen. It is basically a measurement. Okay? It is basically a measurement, and any such thing you can call it a measurement. But for us, we have defined. I mean, we have defined measurement in two ways. Which is just a completely positive map from some non-commutative algebra to commutative algebra, which we called as RC of something, called as measurement. That's one generalized one. Or you can take, I mean, the minimal one is you take a random variable and measure with respect to spectral projection. So which you can, there is something called slightly more general measurement using operators, which is called POVM, positive operator valued measurement. Okay? So POVM, this is definition, positive operator valued measurement. Okay? This is given by, I mean, POVM is given by mx, x in some set, which is our classical space. X is the classical set, okay, such that mx are all positive operators. You can have mx equal to some kx star. I think kx star only, not kx star, kx star. Okay, such that summation mx should be equal to the identity operator. One is the identity operator. So this is what is called a positive value measurement. How does it measure? Then the probability of any random variable, any row. I mean, the probability of x equal to x. Probability of x equal to x. I mean, there is no x here. So what I want to say is, you can define x using this. But I mean, if you have pi, you can define summation. This lambda I is this set kind of thing. So the probability of x. But let's just write it. Probability of this set x. Okay. Probability of this set x is the trace of mx rho. That's all. Okay. This is positive, so this gives the number which is 0, 1. Okay. And if you take the sum of these probabilities over x, it will be 1, because trace of rho is 1 and mx add up to 1 because of that. Okay, so this is, oh my god, I haven't changed. Please tell me. Sorry. I'm sorry. Well, we haven't done much. So this is just the computation for the classical quantum channel for the trace preserving one, and this is the Chai matrix of that, which I've explained. And I had actually had something written here on what is that, gamma, the maximal entangled state gamma, which you usually write it as I tensor I, right? Summation over I, which you can actually write it as ek bar tensor ek bar. Okay. If someone watching through the video, you can actually understand by keeping one of the sound on one screen and video on the other screen. Okay, I mean, this board, actually I have erased it, that one cannot see. But anyway, which we have done it before. Did we do it before? We have done it before. We have done it, no? So if you have any unitary u bar tensor u of gamma is gamma itself. So because of that, you can write the gamma in terms of maximal entangled state, not just using standard orthonormal basis, by any orthonormal basis. So from that, it will follow the Chai matrix actually doesn't depend on that. We are not using it, but we can take this as the standard basis if you want. Okay, so that doesn't matter. Anyway, quantum classical channel is something quantum classical channel is basically a measurement. So for that, but we use something called a generalized measurement. POVM, which is positive operator valued measurement. For that, we have a set of positive operator MX, such that MX adds up to 1, and MX are positive operators. Then the probability of any singleton X is given by this. So this is a probability distribution you can see. So it will take a quantum state rho to a probability distribution given by these numbers on this. So that's what it's called classical quantum classical channel. Okay. Hmm? No, nothing. This immediately gives, no. There is nothing to do. No, there's nothing about commutativity. We just get some numbers. If you want, you can, this may look like trace of this times, I'll just write. When we write the channel, it will be clear. Okay, what is commutative will be clear. It is just the numbers we need. Okay. So definition, N, a quantum classical channel, okay, from A to B, is an operator which takes a quantum channel rho, okay, rho A, to be summation trace of given a POVM, or given a POVM, positive operator valued measurement, MX, X in X. Okay. We have an HB equal to span of this X in X. Take it. Then you get MX rho, this numbers, then this. That's all. This is classical. Okay. You just get a diagonal matrix. Okay, that's all. There is nothing. This MX has nothing. MX is in a different space. We get a probability distribution in a different space. Okay. This has nothing to do with the commutative of MX. So this is what is called a quantum classical channel. Okay. Now we can actually compute the Krauss operators for this. So it is landing up in X. Okay. So we should have X here. And if rho, no, we have to talk about MX. If MX is equal to lambda X, okay, I lambda Xj times some Xk, Zk. Okay, MX looks like this. A summation over J equal to 1 to Rx or whatever. This depends on X also. So then if this, then we want to define the Kx. Kxj. We have to take the square root, of course, lambda Xj, if you will get. And this is easy guess. Okay, we have to get the X here. And we have, obviously, this is what we should have. Xj. This is what we should have. This is also rank 1 operators or the Krauss operator. Okay, this is Kxj. Now we have to verify. So so we will come to that. The first verification is summation Kxj some rho Kxj star. Okay. That sum is over X in X, J equal to 1 to Rx. Okay. Okay. Let's write it. This is equal to, so the lambda X will squared and it will be lambda Xj. Then we have X and Xi Xj. Okay, that's what we have. And we have rho in the middle, and that will be flipped. So Xi Xj and then X here. Correct? Right? Okay. Okay. Now, not rho. Yeah, rho, this is correct. Okay, summation over x and then j. And j from 1 equal to 1 to rx. Okay. Okay. Rho of so summation over j equal to 1 to rx. We keep the summation of x outside. Okay. This xi xj rho xi xj, here lambda also, lambda of xj. That's what we have there. Yeah, this is just trace row. Wait. Yeah, I mean, this is just, I mean, mx acting on xj is lambda jx, right? So you can bring the lambda x here. Okay. You can bring the lambda xj here. Lambda xj acting on this just mx, right? They are the eigenvalues for mx. So this is just, then it is just, these are orthonormal basis. So this is just trace of rho mx. So what we get is the summation is equal to summation over x trace of rho mx xx. So this is what we want. Similarly, we want to take, this is our k, xj star xj. This is to verify that this is trace preserving. Okay. So for something to trace preserve, some CP map to trace preserve, this should be equal to 1. Okay. So let me just do it here. If we just flip it, okay, anyway, I'll do it here. So this is just going to be summation lambda xj, then xi xj. So kx, no, it is just this way, no? Kx bar. So it is just, yeah. Yeah, xi xj, correct, right? Is that right? Yeah. And then x becomes like this, okay, x. And then this becomes x here, then xi xj. Why should it be 1? So, okay, xx is 1. Then if you add over lambda jx, no, that is just rho, no? We should get 1. Kx star is going to be xi x flipped this way, and the x xi xj. So summation over, the summation over j is inside, summation over x is outside. Okay. So you have to sum over j first. Okay. Yeah, sum over j first, you will get mx. Summation mx is 1. It's because of that. You will get mx. Okay. This is equal to summation over x, mx times xx, which is 1. Okay. X is not, which is 1. So a summation of mx only, that is equal to 1, operator 1. The 1 is the operator 1, identity. So because of that. It's clear, no? So if you sum over this lambda, I mean, this is a scalar, which is 1, you can remove it. Then lambda x, say, which is equal to mx. Summation mx is 1. We have assumed summation mx is 1, that's why. Okay. So we have done. So these are the cross operator, and this is trace preserve. Okay. So we want to compute the Chai matrix. So you compute the Stein spring. Okay. Stein spring should be clear from that. We want to compute the Chai matrix. So our N is from HA, which is our quantum space, to HB. HB is just the classical space with, generated by the vectors X. Okay, and one tensor N is of course from HA, tensor HA, sorry, L of HA. This is L. Sorry. Okay. Is from L of HA, tensor L of HB, to L of HA, tensor L of H. Sorry, this is A, to L of HB. Okay. And one tensor N. So what you have to do, we have to compute it on some ij, okay, ij. So let's just compute this I, j, tensor I, j. Let's compute this. Okay, we have to sum it. That's what our Chai matrix says. We have to sum it over ij. That's what Chai matrix. Okay. So this is just I, j, tensor. So what is how is it defined? This is trace of, this is our row now. The trace of this times xx. Okay. So trace of mx. Okay. I mean, we have to have summation mx, right? Summation mx. We keep one mx. So this is yeah, summation over x in x. Wait. No. Where is ij coming? Ij. Yeah, this has ij, that has xx. So this will land up in, yeah, this will land up. So this will have ij, trace of ij, mx times xx, right? This is what we get, right? This is what we get. Okay, there's a summation here. So summation, we take summation outside. Okay, ij. Okay, tensor. This trace of this is equal to, this is just the inner product of mx. You bring the I here. Okay, mx j mxi. Okay, right? This is just the, you can bring this operator here because it's a trace. Okay, then j inner product mxi. That's what you have. And this is a scalar, so you can remove the trace. Trace times this. Okay, so we got this. Now this is just mx transpose ijth entry. Mx transpose ijth entry, which you can bring it here. It's just a scalar, you can bring it here. So which is a summation xx. Okay, mx ijth entry. Okay, I mean mx transpose ijth entry of ij. If you want, you can write it in terms of inner product. Okay, tensor xx. Okay, so now you want to consider the Chai matrix. That is one tensor. Chai matrix is this, right? One tensor n acting on summation of this ij. Okay, which I just directly write. Chai matrix is just the summation of this. Summation over all ij. If you take the summation over all ij, you just m transpose x. Okay, if you take summation over this, so only the summation over x will remain here. Okay, because if you take the summation over ij, you get mx transpose. Okay, so summation of x here, you get mx transpose here, tensor xx. That's all. This is the Chai matrix. Okay. Mx transpose tensor xx, summation over this. Okay, it's clear, no? This is because you get the transpose ijth entry of the transpose times ij. If you sum it over ij, that's what precisely mx transpose is by definition. Sum is over ij because of that. Okay, so this is quantum classical channel. We have done this. There is something called quantum instrument. What is quantum instrument is, there's something called collapse of, when you do the measurement, you get the collapse. Okay, and there is an expected state after the measurement. So this is what we want to do. Okay. So this is what we are going to discuss. Quantum instrument. Before that, we want to talk about the collapse postulate. Collapse postulate is if a POVM, positive operator valued measurement is performed, then and you measure the state X, and if the state X is measured, X in is the outcome. We are not going to use it, but this outcome we will use it when we construct channels and something. So X is outcome. Then a row collapses to, I mean, we are measuring the row basically. A row collapses. We are measuring row with respect to this Mx. Okay. We have a collection of positive operators, Mx, finite collection of positive operators. Then we measure this row with respect to that POVM, and suppose X is the outcome. Then this row collapses to this Kx row Kx star, where we have already used this Mx equal to Kx row Kx star. Mx is positive operator, it will look like this. But this is in a tracial state, so we have to take the trace also. Okay. So this will collapse to this state. This is the state, again a state. Positive operator with trace 1. Okay, because we have divided by this. It will collapse to this. So this is the outcome, collapse postulate. We can talk about expected state. Expected state will be an average kind of thing. Expected state after measurement. Is summation Kx row Kx star. This is different from row. Okay, Kx. So if Kx are commuting, you ask, it will be in different blocks like that. Or one can, you want to say this doesn't remember the X. This just sums over this. If you want to remember the X also, or you can write it like that, summation Xx tensor set Kx row Kx star, if you want. Okay. So this is the general nonsense about quantum measurement and other things. But notice that this map, X going to Kx row X star, this is a completely positive map. It's not preserving trace, but it doesn't increase the trace. It can decrease the trace. I mean, it decreases or it may be equal. If it is equal, everything else should be 0. So it's a non-increasing, this X row going to Kx row Kx star. This is a non-increasing CP map. Okay. So suppose this is different. Suppose Mx. This is script X. Mx from L of HU to L of some L of HA to L of HA itself, right? I think it should be to L of HA itself. Well, we can take it to some other thing also. Okay. Doesn't matter. Okay. Such that summation Mx, okay, X in, suppose Mx for X in this. Okay. Summation Mx is a quantum channel. It's a channel. Okay. Of course, summation is a completely positive map. It has to preserve trace. okay, is a channel. Then m of rho equal to summation mx rho, okay, x in this. This is what is called x is a quantum instrument. Okay. You can instead write it as m rho. You can write it as summation this tensor mx rho. Then it will remember this. Okay. And for this, of course, depends on mx. Each mx cross operator, you can write the cross operators. You can, I mean, it's all easy. Okay, I will not do that. Okay, so this is something we will be using it. Maybe this course or later course, I don't know. Okay, depends on, I mean, if I give second part of it, then we will discuss it. Okay. Okay. So now we want to discuss something new. So these are all different types of channel. Now we want to talk about some particular kind of channel. Okay. So what is called entanglement breaking channel. It breaks if there is any entanglement. So it gives a separable state. Okay, entanglement breaking channel. There are some important kind of channel which is used in quantum communication. Okay? Entanglement breaking channel. Okay. So definition: n is from L of HA to L of HB. Is said to be an entanglement breaking channel. I use EBC for this, okay, entanglement breaking channel if n of 1 tensor n of rho or A, okay, is separable for all rho or A in L of HR tensor HA for all HR. Any HR you can take, any of course finite dimension. Then you take 1 tensor n, that should take any state to a separable state. If you apply this, it should be a separable state. Okay, that is what is entanglement breaking channel. This definition. Okay. So first one, composing. I mean, this is like an ideal kind of thing. If you compose an entanglement channel in the left or right by any channel, that's also entanglement breaking channel. Okay. So what is a separable channel? Separable is not product state. Separable state means, I mean, is a separable state. You take this state, and if you apply 1 tensor n, it should be a separable state. Okay. So 1 tensor n of any rho or A will look like summation over Pi, some sigma r or I, some sigma ai, right? Such that summation Pi equal to 1. This is what separability means. For pure state, it is product state. Pure state is separable if and only if it's a product state. For a mixed state, these are all matrix, these are all pure state. So this should be like a product. I mean, it is like a linear, convex linear combination of product state. Okay, that's what a separable state means. Okay. Now I will orally tell you that if you apply anything on this, any 1 tensor, some one n you have, suppose you have M and L, some channel. M is a channel, L is a channel. So you apply M on this will give another state, summation PA of some state. Okay. So that will be 1 tensor n if you apply, that will give a separable channel. That will be some summation QA something. But each of them will add up to 1. So the product of that PA something, that sum will also add up to 1. So you will have a big, I don't know what to write, okay, big sum, but which is still a convex linear combination of product state. So that will be so if you apply on the right, if you apply on the, I mean, if you compose with the on the left of any channel. If you compose entanglement channel on the left with any channel, you will get entanglement breaking channel. On the right, it's very easy. If you apply first an entanglement breaking channel, you get something like this. Now, if you apply 1 tens or M on that, it will be a product thing. Okay, so it will preserve trace, and it will look like this. So that's clear. Okay, so if you compose in the right or left with the entanglement channel with any other channel, you will get entanglement breaking channel. Okay. Entanglement breaking channel. Now we characterize the entanglement breaking channel by its Choi matrix. Of course, we cannot go on checking with each HR. Okay. Okay. This is the proposition. N is from L of HA to L of HB is entanglement breaking channel if and only if the Choi matrix, the corresponding Choi matrix, is separable. Okay. Of course, if it is an entanglement breaking channel, Choi matrix is something, 1 tens are N applied on that. So that is separable is clear. So this way is clear. Okay. So we have to prove the other way only. Okay. We have to prove this way only. Okay. So suppose the Choi matrix is this, okay, of AB is separable. Suppose the Choi matrix is separable. Okay. Then for any rho RA in L of HR tensor HA, okay, you write 1 tensor N of rho RA. If you remember, we have proved this. This is equal to, in terms of Choi matrix, we can write this action 1 tensor N as follows. This is equal to, you will take the trace with respect to A, but we'll have a 3 tensor product, which is, this is the partial transpose. T is the partial transpose of rho RA. Tensor 1 on B, right? B. Okay. Now there is 1. This is the tensor on R. Tensor is phi on AB. Okay. Phi of AB. And of course, there is a DA, DB, DA. We will usually have gamma. So since gamma is of, 1 by dA of gamma is this. We want a unit state, no? We want to have a unit vector, the gamma. So we have to divide by 1 by square root of this. So we get, if you apply this, you get gamma. Okay. We proved it for gamma. So for that state. So this is the partial trace with respect to A. A is in the middle, and you have two. This is the 2 product. This is the 2 product in the other one. So 1 R on this. Okay. So you have, this is not, you can't compose these 2. Okay. It is like this. Okay. So this is the formula we have proved. Okay. So now suppose phi A is, phi A is assumed to be separable. Okay. Let phi A be equal to summation pi. So sigma of R I tensor, no, it is separable means it lands up in, no, this is in A and B, no? Sigma of A I, sigma of B I, correct? Right? Sigma A I is the state on L of HA, okay? And sigma B I is on L of H. Okay? And summation Pi equal to 1. They are numbers adding to 1. Okay. We have assumed the Choi matrix is separable. So that's what I'm using. This is P. Numbers P. Okay. Now we have to verify that given that is separable, we have to verify this is separable. Okay? That's what entanglement breaking means. So this is separable. Okay. So now let us apply this. We just have to apply this. So this implies 1 tensor n of rho RA. Okay. That will be equal to we just have to write summation. There is a dk, there is a dA, summation PA. Okay. Summation over this summation is here. This summation I. Okay. dA trace A of rho. I mean trace of the whole thing, right? Write it down. This is equal to. I mean here it becomes a product. You see, dA trace A. See, if you have some HR tensor HB, HA tensor HB, okay, and if you have something separable state, some state tensor some state here, then you are taking the partial trace with respect to this. It is enough to consider this tensor and partial trace. I mean, if suppose if you have some sigma tensor, sigma 1 tensor, sigma 2, then you want to take the partial trace of A with respect to A, middle one. This is on this. Okay, middle one with respect to this. Then it is partial trace of the whole thing on A with respect to A. It is same as taking sigma 2 tensor partial trace with respect to this. That is clear, right? Okay, that is clear. By definition, it's clear. Okay. So I'm just taking the partial trace with respect to that trace A of rho RA, TA of rho RA, okay, tensor 1B. Okay. I'm taking the partial trace here itself. Okay. I've taken the partial trace here and 1B. Then summation, whatever, Pi, sigma AI, tensor, 1 tensor sigma AI, 1 R tensor sigma AI, tensor sigma BI. Okay. This is okay. I have just substituted this. I have just substituted this and used the fact that this is the product state. I have taken this. Okay. Now you define, we keep the sigma A as it is. Okay. Now you define tau of, we want to get a, what do you want to get? We want to get a, we want to show that this is separable, right? After taking this. Okay. So we get a single state. I mean, we are anyway taking the partial trace with respect to A. Only color chalk. There's no white chalk here. I have changed this camera, no? Oh no, the camera is pointing here. I was writing here. I'm sorry. Maybe I could give the camera to you, one of them. I'm sorry. Well, if you keep the video and audio in different screens, it should work. We are just trying to prove that N is entanglement breaking channel if and only if the Chai matrix is separable. Okay. So one way is clear. If the Chai matrix is if it is entanglement breaking channel, then the Chai matrix is separable because that's applying for that state. So suppose the Chai matrix is separable. Okay. Then we can write the Chai matrix like this because it's separable. And we have this formula. We have this formula for any 1 tensor n. We have something like this. So I have just substituted the Chai matrix here. Then I have taken the TA, whatever I have explained, that TA here. Then I get this. So this is unfortunate. So, well, the chart is too. Okay. Not much I haven't said much. Okay. I have just substituted the chi matrix, which is a separable matrix like this. So I have this formula. 1 tensor n of any row ORA is just dA times trace. This I proved in the previous class, which is just, this is the partial transpose of rho RA tensor 1B times PAB. It comes like this. This is the formula we have proved. I have just substituted this, which is a separable state. So we get these two things something. We get TA of, these two things something. So I can take the trace on the first two entries. First, I can take the partial trace, and this is the partial trace on 3 tensors. Since it is separable, I can take it on the first two tensors. So I get this formula. Okay. So I get this. Now, okay. Now this is equal to DIPA. I will just club it together. So this is just trace. No, this trace is taken here. Okay. So this is just 1B as it is. So we have sigma AI, okay, on this sigma BI, sigma BI on this entry. Tensor some tau or A I, okay, summation QI. Okay, let me I will explain what it is. Tau RI RAI QI. It looks like this. Certainly, it looks like this. You have one entry, you have sigma I. The other two things, you have something. Not RA, tau R on this, because you have taken the trace over A. So you get only on R. Okay. There, of course, sigma BI is as it is. Only tau RI I have to explain. Tau RI equal to take the trace A of rho or A. Okay. Rho or A, TA of rho or A. This is partial transpose. Actually, when you want to take the trace A, okay, this is to trace A of TA of this, okay, TA of this times one tensor, one tensor sigma AI. That is what is remaining. Okay, you have trace of this divided by QI. What is QA? QA is just the trace of this. So you get QA here. You have QA here, and I'm just so that this becomes a state. So I have to compute QA, means I have to compute the trace of this. Okay, and QI is equal to just the trace of this. If you compute the trace of this, if you want to compute the trace, this is trace A already you have taken, which is just 1 tensor trace of A. 1 tensor trace. Partial trace is 1 tensor trace. Okay. If you want to trace, means trace tensor trace. So that will become trace of the partial tensor of this. That is, this is just rho R transpose. Or you can keep it as if you want, which is just rho R transpose, where rho R is the partial trace of, partial trace of this. Okay. Rho R transpose times sigma. Yeah. That is rho R coming. Or I can just keep it, doesn't matter. Okay. Trace of rho or A of this times 1 tensor sigma A. Okay. And then there are some scalars. QI is equal to PI, DA, PI. Change the camera. I'll go there. I've just written the okay. So this thing implies 1 tensor n of rho RA, rho RA equal to, so all we have to, sorry, all we have to verify, I mean, we have written it in this form, summation Qi tau Ri sigma Bi, where tau Ri is this divided by its state, so it's a state. All we have to prove summation Qi is 1. That's what we have to prove, okay? So summation Qi, they are numbers which are just dA, Pi, summation Pi, okay? Summation Pi, okay? Then there is trace of Ta of rho Ra into 1 tensor sigma Ai, okay? Sigma Ai, okay. So we can take this Pi inside this, and there is no I here, summation also here. So this is just equal to trace of Ta of rho Ra, okay, into 1 tensor. You can take the summation here, summation A dA Pi sigma Ai. Okay. Okay. Now notice that, see, we have our phi Choi matrix. Phi is equal to summation Pi sigma Ai tensor sigma Bi. Okay. So if you take P, this is in A, trace B of P, okay, that will be summation Pi sigma Bi, right? On the other hand, you have this gamma gamma. If you take the cement trace of trace, I mean, if you take the partial trace of this Choi matrix, you get identity divided by dB. That's clear, no? Partial trace with respect to A, it is just, you just compute it in that summation Ei. You just compute it. So, I mean, the other one, it becomes just identity, okay? Trace of any phi with respect to, if you take the B, which is just identity divided by dA. Okay, identity over B, identity over A divided by dA. So this should be equal to identity. This is A summation. Okay, so this is the discussion we have. Okay, if you have the Choi matrix, we have assumed Choi matrix looks like this. It is a general fact that if you take the partial trace of the Choi matrix, you get summation. I mean, you general trace. I mean, when you take the positive partial trace here, you get this. In general, for any Choi matrix, if you take the partial trace, it's supposed to be this. So this should be equal to this. So summation Pi, this should be equal to identity by dA. dA, when you take dA with respect to it, is just identity. Okay. So this whole thing is equal to trace of Pa of rho Ra. That's all. Identity tensor identity there. The rho Ra. Of course, trace of the transpose is same as this, which is equal to trace of rho Ra, which is equal to 1. That's what we wanted to prove. Okay. I actually wanted to prove one more proposition, but I am tired, and I think it has taken time. I will stop here. I mean, the thing is, I may get confused. Maybe shall I do it? It will take another half an hour. Maybe, okay, I will not do it.